You want to build a box with a square base that can hold 8 cubic feet while using the least amount of material possible. What should the dimensions of the box be? So with every optimization problem, there's going to be something that is fixed, and there's going to be something that you're trying to optimize. In this context, the fixed value is the volume, because it says that the box with a square base can hold 8 cubic feet. That's not going to change. Meanwhile, the thing that we're trying to optimize is the surface area. And the reason for that is because it says we want to use the least amount of material possible. So we are optimizing surface area. Optimizing is all about maximizing or minimizing. So you should look for words like least or greatest amount when trying to figure out what it is that you're trying to optimize. To get started, we're definitely going to want a picture for every problem that we do. So we need to create a picture of a box. So there's my box. I'm such a good artist. I'm just going to put this off to the side. Try to make it not go sideways. There we go. So we know that it has a square base. That means that I can label the square base as x by x. We don't know the height though, so I'm going to use a different variable for that. We're going to call that y. Now we need to create some equations. So first the volume. Volume is length times width times height, which in this context is x squared y. And we know that that's fixed, so we know that it's going to be 8 cubic feet, so I can write it as 8 is equal to x squared y. Surface area is going to be the sum of all of the different areas of this shape. So we have 2 x squareds on the top and the bottom, so 2x squared, plus 4 different longer sides, which we'll call x by y. So now I have my 2 equations. And we're trying to optimize the surface area equation because it's asking for the least amount of material possible. So the equation that we're optimizing is always the one that you're going to end up finding the derivative of. But you might notice that we can't really find the derivative of this equation because there's 2 variables. We have x's and we have y's. So this is where our first equation comes into play. We're going to solve for one of the variables in that volume equation. I'm going to choose to solve for y. So I get y is equal to 8 over x squared. Now we can just use basic substitution and substitute that into our surface area equation for the y. And that's going to leave us with a surface area equation that only has x's on the right-hand side. So the surface area is equal to 2x squared plus 4x, and then we're going to substitute in 8 over x squared. I'm going to simplify so that it's easier to find the derivative. And using our negative exponents. So the first derivative, pretty simple, we're just using power rule. You guys should note though that the derivatives are going to be varied difficulty depending on the equation that you end up with, but there is a lot of basic power rule like this. If you recall from the last unit, we learned that when the derivative is equal to 0 or dne, maxes and mins occur. So these equations are never going to be dne, but we can set it equal to 0 to solve for where we're optimizing our equation. So you're always going to set your derivative equal to 0, and then you can solve. I'm bringing the 32 to the other side, changing it back into a fraction, so x squared's on the bottom. Doing a little bit of cross multiplication, and then we can solve for x. And it's going to work out that x, in this case, is going to be equal to 2. So that gives us our base. Our base is going to be 2 by 2. But we still need to solve for the height of this box. We still need to know what y is. So what's really nice about this is that we actually already have an equation where y is isolated. If you look back at the volume equation, we have y is equal to 8 over x squared. So we can use this. We know what x is now, and I just have to do a simple substitution, plug in 2 for x, and I'm able to solve for y. And it does turn out that y is also 2. So in this specific example, to optimize the amount of material that we're using, the box ends up being a cube. It's 2 feet by 2 feet by 2 feet. And you can check that it makes sense. 2 times 2 times 2 gives us 8, which is the volume that we were looking for.